దానికి మాట్లాడాలి అలా చేస్తాను చెయ్యి పొద్దుపోతాడు.
So, good evening, all. All right, so we start. Good evening to everyone.
Good evening, sir.
Yeah. Okay, so I think we've covered a lot of topics so far. We've got enough background about the course and the contents. We are step by step covering all aspects required for this particular course, and we are in continuation of that. So today we are going to talk about the topic that are directly relevant to the physical design course. It's also a kind of revision uh, in our series that we are extending. So, as you can recall, some of you already have got this knowledge earlier that we talk about what is system on chip and what is application specific integrated circuits. So we are just trying to understand today all aspects of it, and once we go through them, we got the broad understanding of these topics. Then specifically we will understand one topic at a time, and we'll have some practical examples based upon them. So to start with, as you can see, we are talking about, let's say you are a team in a company and your company receives a project. Project is to design a system on chip, right? That is SoC. And when such project is received by your company, it is splitted. This implementation is divided among a large team of engineers. So here on the right side, you see a block level representation about how the system on chip will be designed by a company that has given a project to implement this one. So you can see that this system on chip uh, can be used for wireless application, for optical communication, for internet of things, for medical application, whatever the target area is. This but accordingly the systems on chip, this chip will have some specifications to meet. For instance, it has to it will be used in some application area, like I mentioned, optical communication, wireless transmission. So those specifications will be, yeah, that your chip should work in that area where the bandwidth is some gigahertz or some megahertz, something like that. The processor speed has to be above a certain gigahertz range. Then the memory should be of this megabyte or gigabytes of the size. It should have these many interfaces and so on. So those would be a system specification that will be received by your company or your team, right? And you don't know how things are inside. You see there is a blank box here, so it has got some inputs and it has got some output. That's it. So the task of a design team which has received this project is to understand first the system level specification. Generally this short team, this consisting of very few number of people, are leaders or the managers in the upper level hierarchy of the company, who actually receives the project and who will lay out, who will understand the system specification. So usually they have many years of relevant experience in that particular VLSI field, and that's all. Once that is done, you see inputs and outputs, and in this block you have to design your chip. So what is system and chip? First of all, it will have a memories, this design, as I said earlier. It will have some processors, it will have high speed input output IO interfaces. So the chip will communicate within the blocks. For instance, for example, here is your chip, and then you have these blocks, memory, processor, and so on. So this is communicating, this chip is communicating through this, and also outside communication is also happening here with the chip. So this is, let's say, processor, memory, and some other interface blocks or data path or controller, etc. So all these intercommunications are they are called high speed high speed IO interfaces, right? So this chip will also contain them, and you got to design them. And also it will have some application specific dedicated logic. Let's say this would be analog, RF, or mixed signal block, something like that. So this complete block will be called as SoC, right? So right here in this block diagram, we are seeing that the first thing they will start about describing the architecture. Describing the architecture, we are seeing in the moment what is the architecture. So they will start, the team will start writing some using some programming language, as I mentioned earlier, hardware description languages. So they will, on the top level or abstract level, they will define what the chip is about. Is it going to perform some function? Accordingly they will define, okay, this is, write some code to describe the behavior of this particular architecture. So if it is a processor, they will talk about memory, processor, interface, data path, controller, etc. Once that is done, the one step down is the functional design and the logic design. That is the team of RTL engineers. So they will also take these individual blocks like memory, processors, data path, controllers, etc., and split the work amongst these team. And they will also use these RTL coding and etc. So I have already explained you, once the coding is done, that is then the team uses logic simulator and the logic synthesizer that automatically generates these gates based on the code that the team writes. Okay, so this is called as circuit design part, where you see according to the function code, whatever is written, the automatic gate routing, gate levels schematic is generated. And as we know that this gate level schematic can be implemented by a transistorized circuit. Next step is the physical design team. Now here is the important part. So let us understand what is physical design. As you can see in this block diagram, here these black spots, they are the pads of the chips, input output pads of the chips. I explained to you what is pad. When the chip is fabricated, you got to connect the outside connection inside the chip, and from the chip you got to make the connections to the outside world. Let's say this chip is placed on the printed circuit board, so these pads will be used to connect, to make the connections. Let's say this is the chip and these are the parts, then it will use to make the connections over the PC board, etc. And these blocks, they are functional blocks designed by these teams. Okay, so you see this is, let's say, memory, this is also the controller, this is arithmetic logic unit, something like that, and they are all interconnected right here with these wires. You see these, all these things. So physical design would be basically to have the in this diagram, the physical design team is responsible to take care of these following topics. So this is also the course for you that you are learning, and in this course mainly we are talking and going to focus upon all these parameters in detail with practical examples, and we are just going to have the understanding about other blocks, other steps in the VLSI design flow. So what are the blocks and the steps? Partitioning means, as the chip goes as a design project, it means you have to partition the area. In a given chip area, you are given a certain area, right? In that area you have to fit your blocks. So the team will decide which block sits where, right? Which block. So that part we'll explore in more detail. That is first partitioning. Then the flow plan, right? Flow planning goals, once you partition the blocks, once you partition the area, in this also you actually decide which functional blocks will be placed where. So more or less they are kind of this is called as flow planning. And once you do that, then the placement with the help of EDA tool, you will place each of these blocks in the given area. Once you flow plan, then you place your blocks here to make the interconnection and the routing between them. So you can see here the blocks have been placed and there is a wiring in between them. So tool will do it for you, but you got to understand, because you have to analyze it and because you have to perform some verification steps whether this routing and the placement is correct, and that's the job of the PD engineer. Then there is a clock tree synthesis. So obviously this chip and the blocks, the functional and logic blocks that you have placed, they are called as combinational blocks and sequential blocks. I have told you what is coming. Sequential blocks are flip-flop, latches, which has a clock, because their output depends not only on the present state but also the previous steps. We have seen that. So there comes clock. When there are sequential blocks, there comes clock. And then signal routing. As you can see, these signals are routed here. And the timing closure. When you have many flip-flops, many functional blocks, many latches, all are synchronized with each other through one word, which is clock. So you have to make sure the clock arrives to the particular function or the logic exactly at the same time. So for instance, you have flip-flop 1 and you have flip-flop 2, and the clock here and the clock here is applied, right? But to this master block, the clock arrives 1 millisecond before to the slave block. So obviously circuit will not perform as expected. So that is the job of timing closures you have to make sure, and also the clock tree synthesis. So we'll explore these topics in more detail. So once physical design team, once that is done, what you do is that verify the design, whatever the placement and routing has been done, and you have to sign off. Sign off means the process of sending the chip to the foundry for manufacture. So what you do, you perform DRC, that is design rule check, LVS, layout versus schematic, ERC, electrical rule check. So remember the three words. These skills are asked from the PD engineers in the industry. So these we'll also see how these steps are performed for the once your placement and routing is done. And once that is done, your chip goes to tape out or the fabrication. When the chip is ready, each die is looking like this and is packaged and sent to lab for the testing before it goes to the market, right? So that's the aim of this slide, is to give you a broader overview about a design cycle in the VLSI industry, and in particular the roles of the physical design team will take care of these two subtopics. But although you don't need to understand the details of each section, like I said, the system is specification, these are the top managerial team, and the team with the collective experience of many years will take care of this, how to define. They will decide what kind of processor it is and all that. So of course you also don't need to have a detailed knowledge about how the coding of each block has been done, but and also how the circuit of each block has been implemented. But to have these, all these steps are interlinked, all these teams are also interlinked, they are interdependent, and that's why as a physical design team you got to have a broader understanding of this VLSI flow and some knowledge of each of these teams and the domains. So first thing, when the SoC, system on chip, is to be designed, they called partitioning. Partitioning, because as I said, there are many blocks. As I explained to you, you have memories, processors, high speed IO interfaces, dedicated application specific logics, analog blocks, RF blocks, etc. So many other logics, so many things. So they have to decide partitioning. It means which block will be placed where in a given chip area. So this digital VLSI design, they call it as a partitioning, and the first term that they use is called as abstraction. So at the abstract level, they define what is the architecture. Let's say it is the processor that is to be designed. A big processor with clock frequency in many gigahertz, and it has a memory of this particular size, megabytes or gigabytes. Then it has a high speed interfaces, then it has controller, etc. So that's called architecture. So it's a processor. Then they talk about micro architecture. If it is a processor, then what kind of processor it would be, right? So architecture will tell, okay, this is the function of the system on chip, and system on the chip is nothing but a processor. Okay, and the microarchitecture will also tell what kind of processor it is. We'll see that in a moment. Once the microarchitecture is defined, we know that it's a Pentium or Core Duo, etc. Then they say in that microprocessor, what are the different logics? Of course, we all know the microprocessor will consist of data path, controllers, arithmetic logic units, and so many other blocks, right? So then logic blocks are known, circuit, how each of those logic blocks, whether it's arithmetic logic units, adder circuit, subtractor circuit, which are the part of arithmetic logic units. Then you have a controller, you have data path, you have memory. Memory can be inside this or outside the microprocessor. So how those logics will be implemented with the circuits, because we know that we use transistors to use those to implement those logics. And final, once the circuit design is for each block will be taken place, the physical design team job is to have understanding of each those blocks, how the layout will be performed, how they will be placed, that is floor planning, how they will be connected to each other, that is interconnection, or signal routing. Of course, those blocks, as I said earlier, are also combinational blocks and sequential blocks. So for the sequential blocks, you have a clock for each of those blocks. So PD team will decide and do some verification steps to make sure those sequential blocks are in synchronization with each other. It means there is no clock issue. They will verify the clock's timing and all those things. They will also perform the DRC, LVS and ERC. Okay, so for example, you are designing, like I said, cross 86 microprocessor, and it has different instruction sets, register sets and memory model. Once architecture is defined, you, as I said, microarchitecture telling you about what is the how the architecture is partitioned into different functional units. For example, microarchitecture means your team and the entire team comes to know what microprocessor it is. Is it 80386, 80486, Pentium, Core, AMD? They're all called as microarchitecture, and these names suggest different names, different numbers suggest they are designs with different number of transistors, with different power requirements, with different speed and so on. One step down, first is the architecture, microarchitecture, then we came to functional or logic design. So now this is the RTL team that is deciding and taking care of how these logic blocks are going to be implemented and how these logic blocks or functional blocks are to be connected to each other. For example, each processor will have adder arithmetic logic units. So let's say in that arithmetic logic units, the processor will have arithmetic logic units, and each ALU will have sub-circuit or logic gates to implement addition, subtraction, multiplication, division, all these operations, ANDing, ORing, that's why the name is arithmetic logic unit. So this also will talk about how many bits that functional block or logic block is 8-bit, 32-bit, etc. right? So for instance, you have a different way the adder circuits or the adder logic is implemented: carry look ahead, carry select or ripple carry. So team will decide based on their specifications, right, what kind of logic they want to select. Accordingly they will write the code, because that's their domain to implement this function. Next step down, circuit design team. So obviously once the logic is defined, let's say for the arithmetic logic unit, they decide that they want to take the carry look ahead function approach to design that logic. Then the circuit design will decide how the transistors will be taken, and they will decide whether to implement this carry look ahead logic, or let's say simple addition circuit or subtraction circuit, or a circuit that performs addition or subtraction. So the circuit design will team decide how the transistors can be used to implement this addition and subtraction logic. So they can, as I explained to you earlier, as we know that if you want to design a multiplexer, right, or let's say an inverter, so I have explained to you, you can use compound gate logic approach also, and you can use the tri-state logic approach. For the multiplexer also you can use the compound gate way, because you know how to use the pull-up network and pull-down network using transistor, or the multiplexer can also be used with tri-state logics, or multiplexer can be used with pass gate logic. So you already know what is pass gate logic, what is compound logic, and what is tri-state logic. So the circuit design team decides based on their specification and the requirement how these logic will be implemented using those transistors. So like I said, if they want to implement this carry look ahead logic, they can use static CMOS circuits or the pass transistors. Now the next step down, we are here, physical design team, is nothing but a layout of your chip. So layout of your chip, as I said, you are not going to perform at a time the layout of the entire chip because it's a big design, right? System on chip, it's the millions and billions of transistors, and millions of logic gates, right? And let's say millions of logic functions or functional units. So you're not gonna do that at a time. So let's focus on a simple logic blocks. So logic blocks got of arithmetic logic unit, for example, let's say 32-bit or simple 8-bit. And we know that in the arithmetic logic unit, you have addition circuit, subtraction. The whole block will perform this arithmetic function and some logical operations. What are the arithmetic operations? Addition, subtraction, multiplication, division. And the logical operation is ANDing, ORing, NORing, and inversion, and so on, right? So you got to draw the layout of that particular block because it came from the logic design team and circuit design is also implemented. Now you just have to draw the layout. So as I mentioned, there are some analog and RF VLSI blocks also. That is the task of another team. Okay. So second part in the design partitioning, when the system on chip is partitioned, the first part, as I explained, was abstraction, and the second part is called as structured design. Okay, it's called as structured design right over here. So what we understand, there is also always a hierarchy. So let's say system on chip is a large system that got partitioned hierarchically into the multiple cores. Multiple cores means it got partitioned into, okay, there is a processor here, there is a memory here. In the processor you got these high-speed input-output interface, you got the data path, you got the controller. In the memory you got some other functions here. So each large system will be partitioned hierarchically into multiple blocks. Those multiple systems or subsystems is called as core. So you will often hear this word in the industry, they call it core, design core or core design. Okay, and each core is built from various units, like I explained. Then each unit is built from multiple functional blocks, and each functional block is built from multiple cells. From the cells, what is cell? The cell is the unit design of inverter, NOR gate, NAND gate, latch, multiplexer, etc. that you call it. Using those cells, you implement higher blocks. And so you see one by one, and finally cells, they are implemented by transistors. So all these steps you already know how things are there. Look, we are going from transistor to the system of chip. A simple one transistor, from here we are going to a system of chip with the billions of transistors, with the billions of logic functions. So this is how the next step that is implemented in a structured way. So that's the structure that gives you understanding about the complete system, which is systematically structured into multiple cores, hierarchically arranged, into multiple functional blocks, hierarchically arranged, into multiple cells, and into multiple transistors. So as I explained to you, once the block is designed, each block is designed, it can be used in many places. They call such kind of action as intellectual property, IPs, right? So next time when your company receives another project, let's say for example, so and many of the system specifications are same, for instance, and only few changes in the next project. So what your company and your team will do, use those already designed blocks which are placed already and stored in the library, and they only have to do some modifications, arrangement and verification steps. So because those IPs, those cores are already designed, they just take them back and use them to connect them to build a next system with little bit different specification, right? And this is a graph way in which we can understand this concept of how the system on chip design is partitioned. So there are three domains. One is called behavioral domain, one is called structural domain, and one is called physical domain. So let's see from this graph and try to understand. So structural domain, we start with the transistor. Transistors are used to build a unit cell. Let's say if I use two transistors to make an inverter function, right? We know how to use the pull-up logic and pull-down logic. Using that inverter, NOR, NAND, multiplexer, latch, flip-flops, I can implement. I go to connect them, counters, registers, and I go to connect them, implement my registers or the arithmetic logic units, ALU. Using them, I go to build a processor. So you see, I start with the transistors and I can design a whole processor. That is called structure of the chip. Here I see a behavioral domain. Behavior in the sense, I know what is the logic function I want to implement. So I know what is the behavior of Boolean equation. So for example, you already know now, if I talk about y equal to a bar, so that is, I don't know how this system, how this logic will be implemented. I have many options, but what I understand, it is just a behavior of logic, right? So y equals a bar is the behavior, that is what I know. And once that is done, I can get the module description. Once I know that, I can have, like, let's say A or B or C and a bar. So you see, this already designed block I can place here, and I can interface or connect them with this another block. So with this simple Boolean equation, one step ahead, I go to build the module. Just a behavior. Here also I am describing the behavior. Here also I am describing the behavior. Once I have so many logic functions, let's say it's a typical blocks, typical logic equations, which are like, and so many complicated functions I can write here, right? So this is the behavior. So then I have to take care of one more higher level. This is called a finite state machine. So I define the states A, B and C in the digital logic, and then I say that, okay, input is 1 or 0, then output, this state is connected, jump to this state 1 or 0 or something like that, right? So this is called basically a finite state machine. In the digital logic design, they also use this, but generally this is not anymore used. They basically just do the RTL coding nowadays. And one more step is the algorithm. They write some programming, like I said, you have a hardware description languages to define them. And third domain that we are talking now is the transistor, right here, and that is called geometrical physical domain, which is your domain because you are learning this course, right? So you already know what is mask. They are a set of layers to define the areas on the silicon wafer in which the transistor and hence your circuits will be fabricated to implement a particular logical function, and hence a particular module, and hence a particular core and hence a particular microarchitecture and hence a particular architecture, which is, let's say, of processor. You see, you start with transistor, go to mask. Cell placement. So like as I just mentioned, you already know cell placement. You have a chip and let's say you place inverter here, you place NOT gate, NOR gate, and then you make them a bigger unit, that is ALU, right? Something like that. Then you have another way to place your cells and connect them together to make another logic. So that is cell placement. Then you have a module placement. It means cell placement is just a unit cell. Module placement, when you connect the cells together, they become module. When you connect the module together, you go to chip placement in the bottom right here. So that is how you basically start from cell to module and finally you go to chip floor plan. An entire chip is laid out. For the layout for the entire chip is carried out. This is called as geometrical and physical domain. So we'll explore these aspects practically, but the purpose of today's session is to give you a broader overview about the VLSI design flow and how things are carried out. Let's say now you are designing a microprocessor. So that is a case study we are doing, and the task is to design a microprocessor. So first, you know already how the architecture is described and how the microarchitecture of the processor is described. Architecture means, okay, you came to know it's a processor chip that we got the project about. Microarchitecture, you got to know that, okay, it's the Intel Core or Pentium. The type of processor, the architecture of processor, you got to know what it is. It means from that you came to know how many instruction sets it will have, what will be the clock of this processor, what will be the memory, how the data path, how the controller logic and everything will be implemented. Then you consider the logic design and you discuss what code and hardware description language, programming language you will use to describe that. So you can use VHDL, you can use Verilog, you can use system Verilog. There are different programming language in which at the top level the description of the system is defined. We know that ultimately the processor is nothing but an interconnection of billions of CMOS or millions of CMOS circuits and billions of transistors. It's a transistor level design, right? We know that. And the physical design of this processor is nothing but the job you are doing, which is the job of floor planning and how much area the chip will take, the final area. And you will then verify your design at each level of the hierarchy for each element of the design, right? And accordingly, just a minute. See here. All right, so after that you draw the layout is nothing but the mask so that the chip will be manufactured, packaged and tested. And when I say your team will draw the mask, it's not essential that you have to draw the mask for each transistors or each cells or each modules. No, the tool will do it for you, like I said several times. But your job is to verify whether those mask placements, their routing, their interconnections, which is nothing but a routing, the parasitics, that's your job. So that task is called as verification, physical layout verification. That is, and you will use a library of standard cells, NAND gate, NOR gate, and inverter. Using these basic cells, you are going to create a bigger logics by interconnecting them. Right? We already know that using logic gates you can create flip-flops, latches, counters, registers, arithmetic logic units, and so many other blocks. There is one word you can hear as you progress. It's called as word slice. It's nothing but built from standard cells such as adders and the registers, multiplexers, and flip-flops. So when you build a particular functional unit using these standard cells, you call it word slice. So just remember that word. So hardware description language, I have also explained you that the team, the design team, the logic design team will use a set of programming languages that is called as hardware description language to define and implement the hardware. In software industry, you use coding to implement your software, and in VLSI you use coding to implement your hardware. Okay, so what exactly HDL is basically a coding to specify the design at a high level of abstraction. It means if I want to implement a circuit or a logic which will perform the job of addition, simple, I have, let's say, 2 bits A and B, and I have to these are the 2 inputs which can have 4 combinations, 0 0 0 1 1 0 and 1 1, and I want to Can you hear me?
Yes, sir.
Yeah, on which slide I started explaining the topic?
Structural design.
Can you structural design, right?
Yes,
Yes,
sir.
this slide?
Completed, sir.
Okay, completed. And this slide also case study?
Yes, sir. Completed.
Completed. This is also complete. Hardware description language. Here are we? Are we here?
Yes, sir.
Okay. Sorry for the interruption. There I got a bit of misunderstanding about. I got some message about the participants has enabled the transcript, something like that. Did you did something? The participants, are you doing some settings there? Just a minute. Huh? Let me share once again with you. Okay, so let me just yeah, there is some caption coming here, like why is that so? Who enabled the caption? Did anybody enable this caption? Yeah, I just got the message here, and yeah, please don't do that because I got disturbed and see this whole flow. If you have question, just unmute yourself and ask me that, right? Yeah. So yeah, I can't see now. That is fine. That is okay. Okay, I share it now again. Alright, you are able to see me now, and we are continuing here. Okay, if you have questions or comments, just unmute yourself. That's the option you have, or just type a message, right? You know how to use the Zoom meeting and all that, right? Don't do any setting changes because the message comes to me and then I get disturbed here. Alright, so we continue here on these slides. So I have explained you about, I just mentioned you about the hardware description languages. So what basically this logic team will do, they will write a set of codes to define their logic. And let's say I want to implement a logic which will add 2 bits. A and B are the inputs. So I have 4 combination of inputs. So HDL, they are basically just telling what this logic is doing. As I said, is the logic of addition. I want to implement addition logic. Then there is a tool called as logic compiler, right? So basically that compiler, when you write a code, that code can be verified by that compiler tool, and you will see some kind of set of waveforms like over here, and the designer, logic design team, will verify this design. For example, what are the inputs, what are the outputs. If there is a clock also, they will also see the waveform for the clock and accordingly clock if the gates and the logic is performing or not. That is the job of the logic design team and the HDL, hardware description language. Once this verification through the waveforms analyzing is done and through the code is verified, then another set of tool is called a synthesis, logic synthesis tool, that will be used to take that hardware description language code into account and directly generate a circuit out of that or logic out of that. So the tool will decide which logic gates, which unit cells to take, and accordingly they will directly synthesize or create the gates or circuit from the HDL. So as I said, there are most 2 popular languages is Verilog and VHDL. So as a PDT, you only need to have a basic understanding about what is the code look like, how the code is synthesized to generate the netlist and the circuit or the logic gates, because this is the information that will come to your team, that will be passed on to your team to take it as a reference and accordingly use a mask to implement this logic, right? I hope you are understanding this clearly. So there are 2 ways to design and define and specifying your hardware for a particular logic. One is called as structural and one is called as behavioral. Remember these 2. Behavior in the sense, we go here. So for example, I want y equals D0 S bar plus D1S. Can anybody tell me, recalling, what is this logic function is of?
2 by 1 max.
That's very good. Can anybody also explain me what are the different ways we have seen to implement this logic? We know,
Passive.
correct. We can also use tri-state logic, but let's say these two logics we know, right? So when I just write a code to define this behavior, what I want, y, output y should be equal to when s bar ANDing of s bar with the data input d0 or ANDing of s with the data input d1. So I don't care how this logic will be implemented, whether it is using compound gate or whether using pass gate. I will let the tool decide it for me. Okay, so that when I write a code to just implement this behavior, that is called as behavioral HTML. So it will tell what is this cell doing, as one of you just answered, this cell, and I will call it as a cell. This cell is 2 by 1 max. So that's it. On the other hand, I write a code. If I write a code where this cell is where the code will specify how this cell is composed of some specific gate and the transistor, for example pass gate transistors or the compound gate, that code is called as structural HTML, right? And then as a designer, I am deciding and I am dictating the tool, use the compound gate logic or pass gate logic to implement this cell, right? So you remember the difference between these two. Here in the block diagram, as you see here, also you can see the behavior means it's just a Boolean expression, and the structural is we are telling what components to be used. We are defining in the code what components to be used and how they are interconnected to implement that, and both will implement your physical mask implementation. Okay, so like I said, logic simulator is to generate the waveforms based on the code, and logic synthesizer tool is to generate the gate level netlist or gate level schematic, and indirectly the transistor level schematic to have such kind of implementation, right? And the layout will also be, layout engineer or the team will use this information as a reference to generate their layout automatically and use the place and route PNR tools or PNR steps to implement this logic. So that was all for today. I hope I gave you a broader understanding of today's logic and the design. In case you have any questions, you can ask me. So before that, I want to again add, so today's revision was about the broader, giving you a broader understanding about VLSI flow. That is what we learned. We also learned when the big system on chip project comes to the company, how this project is splitted, right from system specification to the bottom at the transistor level. And we also understood what the logic design team will do, what the circuit design team will do, and what the layout team engineer will do. And in the next session, I will tell specifically the jobs of PD teams and their tasks. Any questions you have, let me know.
Sir,
Yeah.
sir, does PD engineer will design layouts, sir, like CMOS NAND gate, CMOS transistor? full layout like and verify output.
Yes, you will design for the full layout. Like I said, if there is a big chip at the system level, it would be partitioned into different blocks, and only one of that block, let's say, comes to you. Then your job is to have a physical design of that particular block. Let's say it's a controller block or data path or arithmetic logic unit, for example. So you will design that yourself. You will draw the mask for that particular module or cells, using the cells and the transistors you have a knowledge about and the skills about. Any other question? Are you getting that what I am explaining to you?
Yes, sir.
Yeah, hope. So I think we are going pretty well, and I hope you are getting the basics, intermediate, and some advanced concepts that you will use in your practice, and they will be useful for you, right? So is tomorrow off for your companies or colleges or whatever, wherever you are working? Is it off for you tomorrow?
Yes, sir. Yes, sir.
All right, so we will not have any class tomorrow, okay?
Okay, sir.
Note down, don't ask again. I will just inform that your institute and all that, okay?
Sir.
Yeah.
Hello, sir. Sir, can you send us the previous class slides last week?
Yeah, somebody see. Don't you see the slides I am presenting you? They are same as what we have already covered, and I have sent you for each sessions. The slides, current slides, are same as that content. There is no difference, and I have sent you slides for 10 sessions already, and that's what
Yes,
we are
sir.
revising. So why you want again? That is the same content only.
Sir, I didn't get 10 slides, sir.
You can ask one of these friends you see here, Anil, Manikant, Chelu, Rama, Kiran.
Okay, sir. We received the 10
Even I
slides.
didn't receive any
Huh?
slides. Even I didn't receive any slides.
What is your name?
Chalwa Rama.
Right. So, are you in a group from since beginning, this batch?
Yeah, this is my 7th class.
How come you haven't received the slides? Do one thing now. Who has all the content so far out of you?
Sir, I'm having only 10 slides.
10 up to 10 sessions, right?
Yes, sir. 10 slides.
Good. So again, the last few sessions that I have gave you a revision about, the contents are the same which we covered in the first 10 sessions, right? So I haven't added even a single new slide into this. The purpose of to give you a revision kind of things for this one. So what others can do, get into touch with Anil Kumar, send him hi email, and you can email them.
Okay, sir.
Is a solution to your question? Is it okay?
Yes, sir.
Yeah. So just ask Anil Kumar. He has Anil Kumar. You can send them, and there is no new content. So whenever there will be new content, I will inform and I will send you all. Right?
Okay, sir.
Right. So we stop here and we will continue on Wednesday. Okay?
Okay, sir.
Okay. Thank you.
Thank you, sir.